Imagine an adult caregiver who needs to know with absolute certainty that her elderly parent took their morning dose of Keppra, a high-severity anti-epileptic medication. We see the exact moment the patient takes the critical medication and securely logs it into a mobile device. In a traditional digital health setup, the mobile application transmits that plain text log directly to a centralized corporate cloud via a standard API. To route the notification to the caregiver, the central server must temporarily hold or decrypt the data. This creates a massive, highly targeted honeypot of protected health information, or PHI. PHI encompasses any health status, provision of healthcare, or payment data that can be linked to a specific individual. Users increasingly refuse to upload raw PHI to third-party servers due to the escalating risks of data brokering, cyber extortion, and algorithmic insurance profiling. The alternative is relying on legacy electronic health record systems, or EHRs, which trap patient data inside fragmented institutional silos. These institutional portals require high-friction logins and consistently fail at providing real-time, cross-platform caregiver alerts. This presents a severe engineering challenge. We have to construct a system that routes real-time telemetry across the internet while guaranteeing the routing infrastructure itself is mathematically incapable of reading the payloads. The solution is the Aura HOS Zero Trust Family Protocol. It utilizes out-of-band key exchanges to bypass cloud surveillance. Achieving true digital sovereignty requires decoupling data transport from data access, rendering the central server entirely blind to the data. The architecture starts at the absolute edge. The patient logs the 8 a.m. Keppra dose directly into the Aura HOS native application. This 3D diagram shows device A, the patient's phone. The plain text telemetry is written exclusively to an encrypted SQLite database running on the local device. The device's native secure enclave or key store generates a high-entropy master key securely bound to the physical silicon. The system utilizes native hardware-accelerated AES-256 GCM encryption to mathematically lock the cylinder, instantly scrambling the plain text log into an opaque ciphertext block. AES-256 GCM, or Advanced Encryption Standard with Galois Counter Mode, is an authenticated encryption algorithm designed to ensure both data confidentiality and mathematical integrity. To derive this key, the system uses PBKDF2 with over 600,000 iterations. Password-based key derivation function 2 applies a pseudo-random function to the input password, along with a salt value, repeating the process hundreds of thousands of times to mathematically frustrate local brute force extraction attempts. The strict isolation rules ensure the raw PIN and the biometric unlock tokens never leave the physical hardware or cross a network interface. Unlike cloud-tethered applications, Aura functions as a sovereign medical vault, even during total cellular blackouts. A pure local-first system carries an inherent risk. If the physical device is destroyed or lost, the medical history is permanently eradicated. Avoiding this catastrophic data loss requires a cloud synchronization mechanism, which introduces a direct conflict with the Zero Trust mandate. While edge-computed encryption guarantees privacy, it creates a lost device paradox that can only be solved by a cloud sync layer that does not rely on trust. We resolve this with an architectural compromise: the sovereign node orchestration layer and the Supabase managed backend. Looking at this network topology map, we see device A pushing the locked, scrambled cipher-type block across the internet to the central cloud database. The server receives and stores the payload, but it completely lacks the hardware-derived decryption key left behind on device A. These routing nodes operate as isolated Proxmox virtual machines on restricted VLANs. Virtual local area networks partition a physical network at the data link layer to isolate traffic and prevent management plane compromises. We define this architecture as a blind ciphertext relay. The backend is utilized strictly for routing and storing mathematically unbreakable noise. This enforces Law 2 of the OS Manifesto, the law of zero trust arbitration. Institutional trust requires absolute cryptographic blindness from the software creator. This architecture mathematically prevents cross-tenant data leakage. Even if a malicious actor bypasses the Supabase row-level security, they only extract noise. The data is safely backed up, but this introduces a new operational hurdle. The remote caregiver currently has no way to read it. The remote caregiver receives the alert on their phone, but without the decryption key, the interface cannot render the medical telemetry. Deploying a blind server solves the cloud backup privacy dilemma, but forces the system to find a way to share keys between users without using the internet to do it. The remote caregiver needs the decryption key, but transmitting it through the Supabase server would instantly destroy the zero-knowledge architecture. The solution is the Out-of-Band Key Exchange, operating via the transient Handshake protocol. To solve this, the caregiver physically scans the patient's device in the real world to establish a direct circle of trust. In this diagram, device A generates a localized ephemeral token and surfaces it optically as a QR code, which device B scans. The asymmetric decryption token moves directly from screen to camera lens, completely bypassing the cloud server. This local exchange allows the caregiver's application to securely link to the patient's data vault using cryptographic proof. A continuous, autonomous loop is now in effect. Device A silently pushes encrypted telemetry blobs to the sovereign node. Device B pulls the scrambled blobs from the server and applies the locally held air-gapped key to decrypt them. The plain text push notification successfully renders on the caregiver's device. Optical key exchanges allow absolute endpoint verification, proving that families can achieve real-time synchronization without surrendering trust to the transport layer. The architectural loop is complete. Edge-based AES-256 encryption, routed through blind Supabase relays, and unlocked via out-of-band handshakes. Being mathematically incapable of decrypting the vault alters the regulatory burden for software vendors. The traditional healthcare regulatory framework is dictated by the government's strict data handling requirements. Because Aura hosts acts exclusively as a patient-directed access tool and cannot read or maintain identifiable PHI on behalf of a hospital, it mathematically bypasses the need for business associate agreements. A business associate agreement, or BAA, is a mandated HIPAA contract that holds third-party vendors legally liable for protecting patient health information. This shifts the focus to consumer protection laws, specifically regarding personal health records hosted in the cloud. The Federal Trade Commission legally defines a breach strictly as the compromise of unsecured identifiable health information. Because the encryption keys never leave the patient hardware, the data resting on the Supabase servers is legally classified as secured by statutory definition. In a hypothetical zero-day cyber attack, we can observe a breach of the central Supabase database. The exfiltrated data blocks are merely unintelligible ciphertext, rendering the hack useless, while the endpoints remain green and secure. Zero-knowledge architecture shifts the model from institutional data harvesting to absolute patient sovereignty, proving that the safest way to handle health data is to mathematically ensure you can never read it.